Authenticated encryption is the primitive where we put everything together. So the intent of this is to be able to provide both confidentiality and integrity for encrypted data simultaneously. And everything we've done so far will be a building block or tool to get this. And this is by now the central primitive of symmetric crypto. So pretty much if you have to do symmetric crypto, the advice and practice is you want an authenticated encryption scheme, and this is what you should use. So to back up a bit, recall we are trying to allow Alice and Bob to communicate securely over an insecure medium. The adversary is both seeing their communications and able to modify them. And we identified two central goals. One is privacy for the communicated information. And we studied that extensively. We gave a primitive that provides this type of data privacy, and we called it symmetric encryption. So, and then we gave many examples of modes of operations of block ciphers which had the desired security properties. The security property we defined as the right goal is IND-CPA, and some of those modes are things like CBC and counter. Then we turned to authenticity, and separately we gave the primitive required for that. We called it a MAC, Message Authentication Code. It had a different syntax from a symmetric encryption scheme. It's just a family of functions. It had a different security definition, UFCMA. And we gave many examples, HMAC, encrypted CBC MAC, all of which satisfied UFCMA. So if you look at these two goals, one might say from this, well, we've solved both problems. But the difficulty is that we've done it individually, not separately. So in practice, we often want both together. Yet the way we defined MACs, there is pretty much by definition no privacy because you send the data in the clear. And the way we defined encryption, it didn't ask for any kind of integrity or authenticity. So there's many examples one can give nowadays as to why we want both privacy and authenticity at the same time. As one of them, consider security for medical information. So a doctor wants to send some such information about a certain patient to a database that holds patient's medical data. Privacy is important to ensure that the medical records remain confidential, and authenticity to ensure that when the database gets some medical information, it knows it wasn't modified in transit and it was really sent by the doctor who claims to have sent it. So it's pretty clear that you want both these properties and you want them at the same time. And the primitive that does that is called authenticated encryption. We've studied many primitives now, so we kind of know the approach. We will start with some syntax, which says what kind of algorithms or objects make up the scheme. And then we move on from there to some security requirements. So syntactically, the good news is that an authenticated encryption scheme is not a new object. It's one we know very well. It's just a symmetric encryption scheme. So recall that that's a triple of algorithms, K, E, and D. We used to call that SE for symmetric encryption. We could continue to do that. I sometimes call it AE just because I want to emphasize that it's authenticated encryption that we're interested in. Yet no different surfaces in the syntax in that regard. The key generation algorithm, as before, just spits out a random key. Magically, it's then communicated to sender and receiver. Sender runs the encryption algorithm on the message M. It may be randomized and needs to be for IND-CPA. That produces a ciphertext which goes across the communication channel. The adversary can see that and in our new setting even tamper with it. And then the decryption algorithm takes the received ciphertext and decrypts to get back either the original message or our special symbol bot to say something's gone wrong. we want to discuss this syntax of symmetric encryption having two properties, privacy and some kind of integrity. Luckily for us, privacy is already done. We've already defined what we want there, and it's IND-CPA. So half our job is accomplished. We haven't, however, given any sort of definition for authenticity of a symmetric encryption scheme. We did define UFCMA as an authenticity goal, but that was for an object of a different syntax, a family of functions. So that's not going to apply over here. So we will now give some games and define authenticity requirement for encryption. Intuitively, it's quite simple. It just says that a ciphertext is non-authentic if the sender never sent it. It was never created and sent by the sender. And so integrity will simply ask that an adversary be unable to create these non-authentic ciphertexts. As usual, the definition involves a game. So the notion is called integrity of ciphertexts. We start with this symmetric encryption scheme AE with its three algorithms. This is the object whose security we are trying to define, and as usual, it's a public, well-known object. All the algorithms are known to everyone, including the adversary. The game, as usual, tells you the API that it exports different procedures or oracles, and the adversary will call them. It's subscripted by AE because it depends on the algorithms of this particular scheme. Initialize will pick a random key by running this algorithm, and once it's picked, it's frozen for the rest of the game. For bookkeeping, a set is initialized to 0, to the empty set. The key is not returned or exported. This is a symmetric setting like symmetric encryption or message authentication codes, where security crucially relies on the fact that the adversary does not know the key. We can get some idea or intuition about what is happening by first looking here. This tells us what the adversary needs to do to win, and what that is to produce a ciphertext C as an output which the receiver would accept. Simple enough. So how do we measure acceptance? The game will decrypt the ciphertext using the key provided here and this decryption algorithm, and that'll give back something. As long as that something is not the rejection symbol, as long as it's bits of any kind, that's it, your adversary has won. Why is it won? Because whatever that message is now taken by the receiver to be what Alice sent. If decryption was successful, the receiver thinks that Alice sent it. The only way that the receiver would reject the communication C is if decryption returned bot. So if it doesn't, the adversary wins. Okay, that's one side of it. The other side is that the adversary has some resources, which is that the legitimate sender Alice is encrypting data and sending it out. And the adversary should get to see that and see the ciphertexts that go by, maybe from them glean some information about the key or how encryption is being performed under it that would aid it to come up with this ciphertext. As in many previous formulations, we take an extreme version where not only does the adversary see ciphertexts of certain messages, but it knows the messages and can choose them. So it has access to an encryption oracle. It can simply go there, submit a message telling Alice, please encrypt this, and Alice obliges. She runs this encryption algorithm with this key on the adversary supplied message to get a ciphertext. This indicates that encryption is often randomized. And then the adversary simply gets back that ciphertext. So we now see how it's going to play out. The adversary will think what messages are there whose encryptions, if I saw them, would be helpful towards coming here and forging some other ciphertext. So it queries those messages, collects the ciphertext, looks at them, and then perhaps creates some other ciphertext C which decrypts properly. Now, if that was all there was to it, there's a trivial way for the adversary to win. Query some message here, get a ciphertext, and just output that. When finalize gets that output, it decrypts. By the correctness property of the encryption scheme, it will of course recover the message that was originally queried here and will not return bot. So the adversary would win. But that isn't really fair. It's not actually a violation of authenticity or integrity because that message was transmitted legitimately by Alice. Effectively, Alice agreed that that was a message she sent. So if Bob accepts it, nothing has actually gone wrong. And that's why we have this set. What this set does is it records all the ciphertexts that emanate from these queries. And to win, you have to submit a ciphertext that's not one of them. It has to be new in some fashion. And now the definition is interesting and non-trivial. As usual, there's an advantage. The superscript is the name of the notion, integrity of ciphertext. The subscript is the scheme whose security we're defining. The argument is the adversary. And it returns the probability that the adversary can make finalize return true, meaning it can come up with a ciphertext which is new, not in this set, and decrypts to something that's not bought. So one might, and often does with definitions like this, say that it's quite strong. Suppose that a ciphertext was submitted here whose decryption was some kind of gibberish. You might say, well, that's not really a violation of integrity because Bob or the receiver would look at that and dismiss it as gibberish. But we don't want to take risks like that. We don't want to leave it up to applications to decide whether something is legit or not based on its semantic content. It's up to the crypto to make a clear and conclusive judgment about whether something is authentic or not. So all we ask is that the decryption needs to reject unauthentic things, and if decryption does not reject, then it's viewed as victory for the adversary. Since we're interested in both privacy and integrity, the goal, which is the target of authenticated encryption, is just both. So by that I mean that I want a single encryption scheme, a single triplet of algorithms. It has to satisfy IND-CPA on the one hand, so the advantage of any adversary in the IND-CPA games has to be low. Simultaneously, the same scheme has to have the property that is INT-CTX, meaning the advantage of any adversary in the game we just saw is low. These are completely different properties, so each has to be evaluated independently of the other, but in the end both should hold. Okay, let's try to see how we might get these properties. So we already know how to get IND-CPA secure encryption. So the natural starting point is there, and what the question we want to study and understand is really, what about the integrity aspect? How about getting INT-CText? So the first starting point would be, let's just take some scheme which we know as IND-CPA. Maybe it already has integrity. Maybe it's INT-CText secure. So here is cipher block chaining mode, which we've shown and even has a proof of IND-CPA security. Here are the descriptions of the encryption and decryption algorithms. And as per the picture, remember that it runs atop some block cipher E, and then the key K is used to key that. When you get a message, you break it into blocks, and you run each block through the block cipher, but first you XOR with the previous ciphertext block. In the case of the first message block, that's a random value, an initialization vector chosen by the encryption scheme anew each time. Okay, so you run this encryption algorithm, you get this ciphertext. And we're asking if it's INT-CText. So we're asking can you design some adversary that would create a ciphertext whose decryption is non-bought. That's all it needs to do. It doesn't know the key. It can, if it likes, obtain encryptions of other ciphertexts, but in the end, it has to create some new ciphertext, submit it for decryption, and the result has to be anything is fine as long as it's non-bought, the adversary wins. We now see a very simple and trivial reason why this scheme cannot possibly be INT-CTX secure. If you look at this code, you notice that it never returns bought. It's simply not possible. No matter what C I submit, this process will execute and something which is a string will be returned. Indeed, I can submit to finalize any string I want in the role of this ciphertext, and you see this decryption procedure will operate. It will run this inverse on this, add this, and something will come out. Run the inverse of this on this, add this, something will come out. I don't care what that something is, but since it's not bought, the adversary wins. It's good when we do these attacks to make sure we know how to formalize the claim by writing pseudocode adversaries that show us a high advantage. So here, let's do that. My adversary here simply picks a random 3n block string as the ciphertext and returns it. Return means that finalize gets this as input. It never even bothered to call its enc oracle. It doesn't need that. What happens when you decrypt this? All I care is that quite clearly the answer is not bought. And so our adversary has advantage 1. So we learned this simple but pretty obvious lesson maybe, that you have to have decryption be non-trivial. It has to kind of check something so that sometimes it rejects stuff. Otherwise, there's no way you have integrity. As usual, the way cryptographers started approaching this is to say, let's try to modify something like CBC so that we can acquire integrity. And looking at the prior attack, the difficulty was that when you write down some weird random ciphertext, it decrypts to something. So what they do is they add what's called redundancy to the data. Redundancy means that you encrypt in the following way. You take your original message M, break it into blocks here, and you add a new final block. That new final block is some function of the message itself. That function could be very simple. It could just be zeros. It could perhaps depend slightly on the data. It could be the XOR of all these blocks. There are things called cyclic redundancy codes. We don't have to get into that. It could be something cryptographic. How about the first so many bits of some hash function applied to the data? No matter what it is, the idea is that when you decrypt, you check that the message here has the required format, meaning the last block is indeed H of the prior blocks. And if it isn't, you reject. And the idea is that this should somehow ensure integrity. So this is a natural and popular paradigm. So let's look at it in a little bit more detail. So here I've specified in pseudocode how the schemes work. And the way I've done that is to recall that E is our block cipher with k-bit keys and n-bit blocks. Maybe it's AES. And we've also made a choice of this function H, which has n bits of output. We don't particularly care here what H is. We saw some examples earlier, so whatever it is, as long as it's a known public function. CBC is the base encryption scheme. I'll call that scheme SE, and its key generation algorithm is K, and in encryption and decryption algorithms I've written as E prime and D prime. And now I'm trying to define a new symmetric encryption scheme. That's what this construct amounts to. It uses this one as a subroutine. It leaves the key generation algorithm unchanged, and it changes encryption and decryption, and the new ones are shown here. Encryption follows the picture. What you do is you take your message, you break it into blocks, and then you append a last block, which is created by applying H to the message. But once you're done with that, you just CBC encrypt the whole thing. And formally for us, that means apply E prime under this key, get a ciphertext. The randomization corresponds to picking this at random, and return the C. The message is one block longer than this block here when it enters the CBC computation. So the resulting ciphertext here is M plus 2 blocks, right? There's one extra block here, one extra block here. The interesting elements about integrity are in decryption. When we considered INDCPA, we really didn't need to pay attention to decryption at all, but that's not at all true for integrity. It's very important exactly how decryption works, because decryption is the thing that checks the integrity. So decryption gets a ciphertext. You think of it as this whole thing over here. So what does it do? First, it reverses CBC. CBC encryption reversed means it recovers what's on the top over here. So it recovers some M plus 1 block string. The decryption algorithm used is CBC decryption, which is D prime, and this is key. Now, at this point, it's just run this decryption and it will get whatever this thing gave it. What it's now going to test is that the last block of the message really is the hash of the other blocks. That's the integrity check. If that passes, it says, okay, I think this is an authentic ciphertext, so I'll return the message, which is actually this part over here. If it doesn't pass, then I'm going to return bot. So now we have a non-trivial scheme. It sometimes does return bot as we would like. Why would we think this thing works? Well, if we think about how an adversary would try to violate integrity, it doesn't know the key, K. What can it do? Well, it could start writing something down as a ciphertext, submitting it to decryption, and hope that decryption succeeds and doesn't return bot. The difficulty is that if you write down some stuff here, you don't really know what's going to appear here. And when you don't know what's going to appear here, there seems little reason to think that what appears here is the hash of whatever appears here. In fact, this is even true if this is simply 0, if this is redundancy, because given all this chaining going on, how can we ensure that I write down something here such that after decryption I end up with a 0 here? Right? So there's a fair amount of intuition saying that something like this should give you some kind of integrity. However, you're probably getting used to the story that we keep seeing. It's actually blatantly untrue. So this encryption with redundancy fails entirely. What's interesting about this is that it fails so dramatically that the choice of hash function H doesn't even matter. No matter what it is, as long as it's a public function, there's an attack violating integrity. So let's see how the attack works. We give it as an adversary playing the INT-Ctext game. It has access to an enc oracle, and then it has to output something that goes to finalize, and its decryption, if valid, means the adversary wins the game. So what this adversary does is it picks some one block message. It doesn't matter what it is. And then it creates a second block by hashing the first block, taking advantage of the fact that the hash function is known and public. So you have M1 here and M2 here. Now, the key point is that from the point of view of this process so far, M2 is just a block of the message. With that viewpoint, the adversary submits this as a query to encryption. The encryption algorithm looks at this, and all it says is, okay, I have a 2-block message and I need to encrypt it. Nowhere in there does it know or care about the fact that this block is a certain function of the prior block. So it follows the encryption algorithm that says compute H on these 2 blocks, append it here, and run CBC. And so you get this kind of thing here, and this 4-block ciphertext comes back. And then you see what we've accomplished. Suppose we just drop the entire last block. What you're left with here with C0, C1, C2 is just a valid encryption of the message M. Why is it a valid encryption of M? Because it is M together with H of M and properly CBC encrypted. If you run through the details of that, this adversary will have an advantage 1 against the encryption scheme we just defined. So it's a very, very interestingly powerful attack. It turns out that this attack has arisen in practice, a more real-world rendition of it was used to break one of the early wireless authentication and encryption protocols. And the wireless standards have since been upgraded to more secure protocols. It's interesting to ask why it is that designers of wireless encryption standards didn't see an attack like this. It could be that one reason is that they weren't working like us with these well-specified, clear games and models. And so the goal or target for an attacker may have been a little fuzzy. It's much easier to see attacks when you have the definitions we have. Okay, so far bad news. We've looked at how we might design an encryption scheme that has both privacy and integrity. We now know what the two properties mean, but we haven't been successful at actually designing such a scheme. So let's see how we might do that. And the approach here, quite naturally, is to say, look, we know how to get privacy on its own. That's simply INDCP asymmetric encryption. That's a solved problem. We actually also know how to get integrity or authenticity, provided it's alone. That's a solved problem. We can use any UFCMA message authentication code. We also saw that any PRF provides UFCMA. So for simplicity, let's say we use a PRF. But the problem doesn't stop there. We have to somehow see how we integrate these two tools into an encryption scheme that provides INDCtext plus INDCPA. And that problem is called generic composition. It's called generic because I want to think of this scheme as simply some kind of given black box. I don't want to look at its internals. And same with this. And then I want to glue them together in some generic way and come up with a authenticated encryption scheme. One reason to do that is we have a library of choices for this, like CBC with AES, counter with AES, a library of choices for F, HMAC, CMAC, encrypted CBC. And if we can generically do gluing together, then in this table, any entry could be a choice of an authenticated encryption scheme. So let's try to do this. Now, in our analysis of this, our assumption is going to be that this scheme is INDCPA, but we're not going to assume more than that. We're not going to think of it as some specific scheme, and this is the only thing we're willing to assume. Similarly for F, it's not one of the specific choices here at the moment. It's just anything that has the PRF property. Now, it may look like this, it's quite obvious how to start gluing these tools together. And in some sense that's true, but it turns out to be quite interesting because there's a number of different natural ways to do it. And not only are these ways natural, but they've all been used. So different standards and implementations have tried different ways. And we gain quite a bit of insight by going over those different ways. So recall our goal is to build an authenticated encryption scheme from these two given primitives. This scheme, since it's an encryption scheme, will have three components: key generation algorithm, encryption algorithm, decryption algorithm. The key generation algorithm we fix as shown here. Anticipating that we will be using this scheme and this, we need keys for both of them. So what this does is it runs this algorithm to get an encryption key. Then it picks a random key from this space to get a MAC key. And it returns a key that contains both of those two. So the key for my scheme here is a key of this plus a key for this, because I expect I'll be needing to use both of them. Now going forward, it may be worth emphasizing we're not going to rewrite this algorithm every time because it's the same. That doesn't mean this algorithm isn't important. It's a crucial component of the scheme. If you change this algorithm, for example, by having these two keys be the same or dependent on each other, you get a very different AE and very different security properties. There have been three basic methods for building authenticated encryption in a generic way. And what's different between them is simply the order in which the two things are done. There's encrypt and MAC, which kind of encrypts and authenticates the message in parallel. MAC then encrypt, which says first I'll authenticate, then I'll encrypt. Or encrypt then MAC, which says first I'll encrypt, then I'll authenticate. They've all seen usage. So TLS used the MTE method, at least until TLS 1.2. SSH, which is a secure shell login protocol, happened to use ENM. And IPsec, which is a transport layer security protocol, used encrypt then MAC. And all of these are widely deployed and used. So we're going to study them. The way in which we'll study them is perhaps a little different from some things we've seen before. Mostly, we're going to get some practice at eyeballing these schemes and just deciding whether they work or not. It's not going to be required to write down detailed analyses or adversaries, but to just use your intuition and kind of guess and then justify various answers. First, we need to specify the scheme. So here's encrypt and MAC. It's going to build an authenticated encryption scheme. We already know how key generation works, so I'll tell you how E and D work. Remember that they must use as subroutines the algorithms for the two given schemes. Okay, how do I encrypt? My key consists of two parts, an encryption part and a MAC part, and I have input a message M. I first apply my given encryption algorithm with this encryption key to the message, and I get some ciphertext. This could be randomized, that's fine. This algorithm is also allowed to be randomized. So, having got this ciphertext, there's no integrity yet. So what I do is I say, but I know how to get integrity. I can just apply my PRF or MAC to the message and get a tag. And that tag, if transmitted with the message, guarantees its integrity. So what I return as my ciphertext is this ciphertext here and this tag. Note that the ciphertext for AE, for this E algorithm, is the whole thing. It's a subpart, it has this one ciphertext, as a second part it has this tag. How do we decrypt that ciphertext? Well, we get it, we parse it into these two components, and we reverse these operations. So we know that there's a decryption algorithm D prime corresponding to this. We have the key, we decrypt under that, this ciphertext here, and we get back the message. But we don't just return that. Before we return it, we check the integrity part. So we apply the PRF to M, and we see if the tag obtained matches the one over here. If it does, we say, okay, that's authentic, we return M, and otherwise we return bot. Okay, so that's the scheme. The first element probably is to make sure you understand all the algorithms. But once that's done, we start asking whether security is achieved or not. Remember that we want to ask about two properties of AE. We want to know whether it's IND-CPA, and we want to know whether it's INT-C text, privacy and integrity. We know that E prime or SE prime is IND-CPA, and we know that F is a PRF. Okay, so what do you think? Does IND-CPA hold for this constructed scheme? So let's see how we might reason about that. We notice that here, this ciphertext is encrypting under an IND-CPA scheme. That means C prime can't possibly reveal any useful information about the message. We know it won't because we know that scheme works. That would start to indicate to us that yes, privacy is achieved. The difficulty is that the ciphertext contains more than C prime. It has other stuff. And this other stuff also depends on the message. So we have to worry about that. And the interesting thing is that, in fact, this doesn't work. This other stuff allows you to compromise privacy. Why is that? Because remember, we're asking for privacy in the stringent INDCPA sense. And if you remember some of the elements of INDCPA, one of them is that you shouldn't be able to detect repeats. Meaning, if I twice encrypt the same message, you shouldn't be able to tell that I did that as opposed to not having done that. But this tag is a deterministic function of the message. If I twice encrypt the same message, I will see the same tag, and that tag is visible in the ciphertext. So I will know it's the same message both times. And you can take that intuition and actually write pseudocode for an adversary that violates INDCPA. Okay, well, already the fact that that's a no means we're kind of dead because we want both properties. But we can still ask, what about integrity? Did we achieve that? At least to learn if we got that right. We might think we did because we had a MAC T of the message. So f of f sub km returns T, and f is assumed to be a PRF, which is UFCMA. However, again, perhaps a little surprisingly, it's not true. So integrity of ciphertext is violated. Why is that? Because this tag only ensures integrity of the message, and integrity of ciphertext asks for integrity of the ciphertext. The difficulty is that it may be possible for an adversary to modify this C prime here, having been given this ciphertext, in such a way that when you decrypt, the message M doesn't change. In other words, the decryption of C prime doesn't change, but C prime itself has been changed to C double prime. If that's the case, the MAC will still check out. So this will return M, but according to our CTEX game, the adversary would win. And you can give examples where this is possible. I'm not saying it's possible for every encryption scheme, but there exist ones where it is. So not so good for encrypt and MAC. Let's try MAC then encrypt. What does that try to do? It says, okay, we saw that the main issue with the prior design was that giving the tag in the clear is a bad idea, because when you do that, you can violate privacy. But there's a simple answer to that. Let's encrypt the tag as well. So what this method does is it first applies the MAC to the message to get the tag, and then it encrypts not just the message, but the message and the tag. And all this, of course, done under the given secure INDCPA encryption scheme, whose encryption algorithm is E prime. And now the ciphertext returned is a single object, the encryption of both the MAC and the tag. We must look carefully at decryption, because decryption is what's going to determine whether we have integrity. So what does it do? It gets the ciphertext. It reverses encryption under the given INDCPA scheme by applying algorithm D prime. That gives it back a pair. And it parses that pair as a message and a candidate tag. But it would like now to return the message, but before doing that, it checks the tag. So it recomputes the correct tag, fk of m, using the MAC key over here. And if that equals the tag here, then it says, okay, this looks authentic, so I'll return M, and otherwise I'll reject. Okay, so again, the first step would be just make sure going over the algorithms that you see what they're doing and how they work. And then we can ask again, what about security? So what about INDCPA security? What we're asking is, if you see this ciphertext C, can you learn anything about the data? We know that this encryption algorithm is secure. So we know that whatever it creates doesn't reveal anything about the data. And that pretty much, although you would have to do a proper analysis and proof or whatever, it kind of tells us what's going on. It tells us that we have actually now acquired privacy. Why is that? Because all you're providing here is an encryption of something involving the message. The fact that other stuff is encrypted doesn't matter. This is just a blob. It's not going to tell you anything about the message. So good, we made progress. However, the second problem stays. It's still the case that I could modify this C to some other C, call it C star, such that the decryption under E prime would be unchanged. from C to C star. If that happens, that C star would be a way to violate integrity of ciphertext. So we're not quite there. There's still another thing to try. On the prior scheme, we first MAC'd and then encrypted. Why don't we do it the other way? We first encrypt then MAC. So now we start by taking the message M and going back to what we did in the very first scheme. We just encrypt it directly with our given 9DCPA scheme, and we get the ciphertext C prime. Now, at first that may say, okay, we're off to a bad start because we know that the first scheme didn't satisfy privacy. But that was because we had given the adversary the tag of the data, and we no longer do that. We acquire authenticity by tagging this ciphertext. So we take the ciphertext and we MAC it, and that's our tag. And then we provide again, not just the ciphertext, but we do provide the tag in the clear. Okay, we have to again ask how decryption is done. It gets this composite ciphertext here. It reverses encryption under the base scheme, applying decryption algorithm D prime to this C prime, and it gets this message M over here. It doesn't return it directly. It first checks the tag. It recomputes the tag on C prime as here and sees if T matches up. And if it does, then it returns the message, otherwise bot. Okay, so once you've assimilated the scheme, we go through again the two properties. Do we have privacy? Well, we remember that in the first scheme, we lacked privacy because T gave away stuff about the message. But in this case, T is not a function of the message, it's a function of the ciphertext. And the ciphertext has already hidden everything about the message. So if I now compute some additional function on top of it, it's not going to give me more information about the message. Now, all this has to be argued in a more precise way. But when you do that, you see that based on that kind of intuition, we actually do have the privacy. We did get it. Okay, but we had failed twice to get integrity of ciphertext. So what happens now? We have done well. We got it. Why did we get it now? Because the tag here is on top of the ciphertext. Even if I could change the ciphertext to something whose decryption is the same as it was before we changed the ciphertext, it wouldn't help because this MAC would no longer work for the new ciphertext. So again, you need detailed analysis, but it works out. So, well, where are we then? We actually have a nice way with this method to get authenticated encryption. Furthermore, in one shot, we've acquired a whole slew of secure authenticated encryption schemes because we have so many choices for the two base components. Remember, we are building this authenticated encryption scheme on top of two base components. We have many choices for this, many choices for this. So overall, we have many choices for the authenticated encryption scheme. So then some remarks about these designs. One is that maybe in practice, you don't want to increase your key size. So you don't really want to use different keys as subkeys for encryption and MAC because you want your authenticated encryption scheme to have a short key of, say, the same size as an encryption key. It's always possible to do this. You can, for example, take a single key as the authenticated encryption key and derive the other two keys using a PRF applied to constants. And this is provably good. But you have to be careful that you can't just decide to set KE and KM to be equal to each other. If that tends to be error prone, but sometimes it works. This exercise throws at you another particular choices, again, of encryption and decryption algorithms, which are of a kind of CBC flavor. And it asks you about the different properties. Do we have the necessary properties for authenticated encryption, both privacy and integrity? So you are to analyze that just the same way we did in these little examples, but with a little more detail in the sense that when you claim not, we want to see an actual adversary. It's much harder, of course, to very clearly justify a yes answer, but some intuition would suffice. The third question asks, is this actually just an application of one of our methods? And so you have to look at it and say, is it possible to see this scheme as the result of encrypt and MAC for certain choices of the Bayes primitives? So as I mentioned in introducing generic composition, it's been extensively used in practice. All three methods have arisen. So it's interesting to go back and see how our findings play out versus what's actually out there. And SSH use encrypt and MAC. So in our findings, that's completely insecure. But it turns out that done properly, and in the particular context of SSH, it is possible to make it secure. SSL or TLS used MAC then encrypt. We had again decided that was insecure, and that has actually remained so, and it's been a source of problems. If you look at TLS history, there's been a bunch of attacks on TLS arising exactly from the fact that MAC then encrypt was used and from the type of weaknesses we saw. So there was a proposal to change SSL TLS to use and strengthen it, and that would do well. IPsec from the start used the good method, encrypt then MAC. WinZip was an interesting case which used the good method and then was broken. So looking at all these, we can maybe try to see what are the elements that create these gaps between the theory we're looking at and what goes on in practice. One of them is that the methods are not used in the kind of raw form we showed on the slide. Sometimes there are additional things, encodings of the formats and things like that. And that can add security when our analysis might have shown it doesn't exist. Secondly, our analysis was generic. It was saying that secure means it has to be secure for all choices of the two base components, the encryption scheme SE prime and the MAC-F. And insecure means there exists some choice of them that makes it insecure. But in practice, often those choices of the subschemes are fixed. And for those choices, it could be secure even though it's generically insecure. For WinZip, the disparity was just that authenticated encryption was actually not what they needed. They just didn't realize that. So where are we today then? The story of authenticated encryption continues. There's a lot of interest in designing algorithms, and in particular, people want things that are faster than generic composition. Generic composition takes two passes through the data. It needs to first do an encryption and then do an authentication. And there are schemes like OCB that does things in one pass, so it's very, very fast. Gcm is a scheme that's used in TLS, and it's a standard, and there are many others such. There's been a recent competition to standardize these schemes. So it's a very active area with a slew of new work. So let's look at some of the repercussions and what's going on in the community in this regard. So you can see here that by these stack exchange questions, people are asking exactly the kind of questions we've studied. Well, here's someone asking, should we MAC then encrypt or encrypt then MAC? And they want some recommendations. And you can see that there's been some discussion, some confusion. Oh, it's interesting to see Moxie Marlingspike reply. This is one of the creators of the Signal app, a very well-known cryptographer, received some awards recently. So, and then they point to papers and so forth. But effectively, in the end, they kind of summarize the same things that we came up with. So in particular, if you saw a question like this, you should be able to answer. This is a RFC, we saw again RFC are these Internet Engineering Task Force standards, and it tries to define encrypt then MAC for TLS. Remember, TLS uses MAC then encrypt. But at least for TLS 1.2, I don't think this ever got adopted. If it had, it would have been helped versus some attacks. This is a blog which reflects the fact that these things we're talking about are of much more than theoretical importance. There are really serious attacks arising from wrong choices of how you do generic composition. So in particular, this shows you why MAC then encrypt is a bad choice. And they go through a lot of information about that, but quite interesting. This is an even more generic question, again, on Stack Exchange, but something, again, which is somehow, I think, one of the value of the things in seizure, something to which it would be good for us to know the answer. And the question is, why should I use authenticated encryption rather than just say encryption, where encryption here means something like CBC or counter mode? And the answer, of course, is that authenticated encryption provides integrity and the base encryption doesn't. But the more important meta question is that why would I need this integrity? And as this question has been looked at through usage and time, the conclusion we're coming to is that the default usage should be authenticated encryption. You may not think you need integrity, but you probably do. And so it's best to default to authenticated encryption and basically never use encryption in its plain form. So that would have been the kind of answer one might give over here. And you can see this person has answered by explaining everything to them and so forth. This is our friend Matt Green. We saw him before complaining about the CBC MAC. And here he's giving you explanations about how to choose an authenticated encryption mode. So he goes through different modes and he drums in the same lesson I've tried to state, which is that you really should always use authenticated encryption. Don't try to use plain CBC mode encryption. He says people sometimes complain about that because they think mandating it is hard or there are all kinds of other excuses. But it isn't really true. And many of the problems have arisen through lack of use of authenticated encryption. He goes through some attacks and so forth. Then he talks about these dedicated modes, which are OCB and other things like that, and so forth. So mine of information there. This is the GCM algorithm. Remember I said this was a authenticated encryption scheme that you use every day since it's in TLS. And you can see a description of how it looks here. It isn't quite generic composition, but it's close. You can see that it's using counter mode encryption up here, and then it's applying a kind of MAC to it computed over here. So it's an encrypt then MAC kind of design, but done for very high efficiency and various other things. I mentioned the Caesar competition. So this was a competition that was run to try to get new authenticated encryption schemes. And there's a web page about it. You can look at all the different submissions that were made. As usual, they whittle them down. So every time the submission confirmation goes through a new step, some are thrown out and a few remain. And it goes on. And finally, it has concluded quite recently, and they announce winners. They actually had different categories and a bunch of different winners in each. Another look at Caesar is over here. They have perhaps some more readable look at all the different candidates and how far they progressed and what they used and what properties they provided and so forth. Okay, stop there.